Welcome back everyone. In this lecture we will actually begin the representation theory of finite groups. So, let me quickly get into the definitions and so on. So, let us fix finite group G. So, now we want to define representations of G. So, in many books a representation of G is defined to be a group homomorphism from G to GLV. Since we have started with the definition of representations of algebras, so let me actually go through that definition. So, recall that given a finite group G, we will be able to associate an associative algebra CG, which is called the group algebra. So, recall CG is the group algebra which has the elements of capital G as a basis. So, we take all the linear combinations of elements of G. So, let us denote it by, so I will just denote the elements of G by G only and identify those elements inside CG and then continue to use just a small g for elements of capital G. So, the finite linear combination AGG, G in G, and you have this AG complex numbers for all G in G. So, this is our group algebra, the space that we are interested in. So, this is the group algebra. So, now we have actually taken this elements of capital G as a basis of this. So, in particularly this already has a vector space structure by pointwise addition. So, let me just recall how the addition is defined. So, you take the summation AG in G plus summation BG in G. So, basically all we do is just coordinate wise addition. So, then this is indeed defined to be equal to summation EAG plus BGG, and the product is again obtained from the group multiplication that we have in G. So, if we take for example, the basis element G H in G, then the product of that is just given by the product that we have in the group. So, this is the multiplication that we have in the group elements. Same multiplication that we use it in CG, and we extend that multiplication bilinearly to the entire CG. So, that means if we take summation EAGG and then if you want to multiply with summation BGG. So, this is given by summation, then you will get two summations. So, you multiply. So, you want to actually determine what will be the coefficient of H, where H in G. So, then you simply take multiplication of all elements, this AG BG dash, where GJ dash becomes H. So, this is the multiplication. So, this is the addition and this is the multiplication. So, that we have it in the group algebra CG, and the scalar multiplication is defined similarly. So, if we take a scalar lambda in C and then if we take a group algebra element CG in G, so then lambda times this is defined to be summation lambda AG G in G. So, this is how the scalar multiplication defined. So, now if we take a representation, so let rho be a representation of CG. So, that is a group this is an algebra homomorphism from CG to endomorphism. So, this is an algebra homomorphism. So, in particularly if you restrict this row to G, then we get a map from G to endomorphism of G, sorry, endomorphism of V. But indeed what one can prove, the images of this capital G under rho, they all will be invertible, because we have inverse in the group. So, because of that we will have inverse for these images of capital G. So, indeed, so here is a proportion, one can prove that rho G is indeed invertible element for all G in G. So, here is a one line proof. So, given G in G, we know that G inverse exists inside G such that G inverse is identity. So, identity element of G. So, now because of this, now applying rho, you can see that now apply rho, you can see that rho of G inverse is supposed to be rho of 1G, but 1G is actually unit element inside CG. So, 1G is supposed to be mapped to the unit element in endomorphism of V. So, that is going to be exactly the identity map on capital V. So, in particularly we have rho of G inverse, which is exactly equal to rho G times rho G inverse, which is exactly rho 1 V, sorry 1 G. So, which is exactly 1 V. So, this implies rho of G is invertible, and not only that, rho of G inverse is exactly equal to rho of G inverse. So, this implies that all the elements rho G are invertible for all G and G. So, this means, so given a representation from CG to endomorphism of V, we are getting actually a map from G to GLV. Okay. So, given this map from CG to endomorphism of V. So, given this map, we have this restriction map rho restricted to G that actually defines a map from G to GLV. Since rho is a algebra homomorphism, so that would immediately imply that this is being algebra homomorphism, that would imply that this rho restricted to G is indeed group homomorphism. So, that means from the definition of representations of CG, we get a definition of representation of these groups G. So, this is what we are going to call it as representation. So, this is what called representation of the groups G. So, now this association actually defines a map from representations of CG to the representations of G. The map is defined to be, you take V comma rho, which is a algebra homomorphism from CG to endomorphism of V, and you just take this and then map it to V rho restricted to G. So, from here you go to rho restricted to G, which is a map from G to GLV. And for the converse map, given any group homomorphism rho dash, any group homomorphism from G to GLV. So, what one can do, one can actually easily extend this map to CG using the linearity. So, because CG indeed sits above this G, because G is contained in CG, and this endomorphism of V is again contains this GL of V. Now, you extend this rho dash linearly, then you get a map from CG to this endomorphism of V. So, extend rho dash C linearly to CG. So, that gives us actually a map rho from CG to endomorphism of V. So, how this rho is defined? You take the linear combination. So, rho dash is what given to us, which is a map from G to GLV. So, from here extending rho dash C linearly, we get rho. So, that means you take this rho of summation AGG, you define it to be summation AG rho dash of G. So, this is how you get this new map, and it is not very hard to prove. The resulted map is indeed algebra homomorphism. I will leave it as exercise. Prove that from rho to rho restricted to G is indeed group homomorphism. If rho is an algebra homomorphism, that implies rho restricted to G is group homomorphism. On the other hand, if we start with rho dash, which is a group homomorphism, then the linear extension rho from CG to endomorphism of V is an algebra homomorphism. So, this indeed gives an one-to-one correspondence between these spaces. Okay. So, that means you have one-to-one correspondence between the representations of CG and the representations of G. So, now using this correspondence, we can actually borrow all the terminologies that we have defined for the algebra CG. For example, we can define what is subrepresentation, irreducible representation, indecomposable representation, decomposable representation, completely reducible representation, and so on. So, let me just write down the definitions, equivalent definitions here in the realm of representations of finite groups, so that we do not get confused. So, for example, like what is subrepresentation? Okay. So, now onwards, so whenever I call a representation of a finite group, we just simply consider group homomorphism from G to GLV. Okay. So, your representation is just a map from G to GLV. So, this is a group homomorphism. So, now we can actually see that some terminologies. So, V is called the representation space, and then the dimension of V is called the degree of the representation. So, called the degree of rho, and the kernel of rho is called the kernel of the representation. So, this is called kernel of rho. So, now if this rho is injective, then we call this representation faithful. So, rho is said to be faithful if rho is injective. So, this is actually allows us to embed the group inside GLV and then get information about the group in terms of subgroups of GLV. So, that is how the faithful representation actually becomes important. So, now what is subrepresentation? So, subrepresentation is a subspace. So, W is a subspace plus we want all the elements of G to leave W invariant. So, if we take rho of G, so that leaves W invariant for all G and G. So, a subspace is called subrepresentation if W becomes invariant under the action of all elements of capital G. So, this is in a way equivalent to what we have seen before. Maybe you can take it as exercise. So, under that one-to-one correspondence, so let us call it sigma. So, which actually takes CG representations to the representations of G. So, under this correspondence we can prove that sub representation corresponds to sub representations. So, under sigma the sub representation maps to sub representations and the irreducibles maps to irreducibles and so on. So, here in this group representation, again irreducible means if the 0 space and the full space are the only sub representations. In that case we just simply say actually a given space is irreducible. And sometimes we also use instead of sub representation we also use a G-invariant subspace. So, that is the terminology also. So, here instead of this we can also use what is called G-invariant subspace. So, there are many terminologies, different terminologies are used in the literature. So, maybe like I will, because different books uses different terminologies, maybe it is good to actually record the equivalent terminologies. So, sub representation is same as G-invariant subspace. Like I said, irreducible is same as simple representation, and completely reducible, for example, called semi-simple. Completely reducible is same as semi-simple. So, these homomorphisms. So, homomorphisms, they are sometimes called intertwining operators. So, if any other terminologies that comes, and then maybe like if it is used in the finite group representation theory, I will just mention. Again, representation space is also sometimes called modules. So, when we use modules, then actually it is CG modules. So, the algebra is important. So, representations or spaces of G. So, these are all the some different terminologies, like, but they are used mean the same things. Okay. Okay. So, in this group representations, we fix this trivial representation to be an one dimensional representation on which the group elements acts as one. Okay. So, this is the terminology that is again overused. So, sometimes when we are looking at the algebra, sometimes trivial representation will be called where the algebra acts trivially. So, but here in the group language, trivial means it can act as one. So, that is how we are actually naming the trivial representation. So, for us trivial representation of a group G, it is one dimensional representation. So, note that when we take V to be one dimensional, so then the GL of V is nothing but the non-zero complex numbers inside C. So, so trivial representation, so let's denote it by bold 1. So, it is a map from G to C star where all the elements are sent to 1 for all G in G. So, that means all the elements of G act as 1 on this C, the representation space C. So, this is what we call as trivial representation. So, we actually say the group G act on some representation V trivially if all the elements of G act as identity. So, we say G acts trivially on a representation V if all the elements. So, let us say rho is the map, then rho G is identity on V for all G in G. So, if this is the case, so then you call G acts trivially on the representation. So, these are some terminologies that we are going to use in the course. So, that is why we better to fix these terminologies. So, let us actually try to understand what is the meaning of equivalence of representations in this setting. Again, as before, we were interested in actually getting the intertwining operators. So, let us try to understand why the equivalence makes sense. So, for example, let us actually work with some representation. Okay. So, let us say phi is a representation that is given to us. So, that means we have a group homomorphism that is given from G to GL of V. So, let us say this is of degree n. So, the degree of this representation is n. So, that means V as a vector space isomorphic to C n. So, we can fix a basis. So, we can fix a basis, let us say B of V. So, then that is going to immediately give us isomorphism from V to C n. So, by fixing the basis we get this isomorphism. So, this is indeed a vector space isomorphism. So, now it is exactly saying that we have fixed a coordinate system, but when we fix the coordinate system we do not want to actually treat this representation space differently. Okay. For example, like using this isomorphism vector space isomorphism from V to C n, we will be able to actually define an action of G on C n via this phi. So, let us actually try to work out via the maps. So, we have this isomorphism from V to C n, and then let us say given element G in G, we have this phi of G, which is actually a map from V to V. So, that defines a linear map from V to V, and then we have again this isomorphism capital T here. So, now if we are interested in defining an action of G on C n, so what we can do, we can use these maps and then define here the action. So, all we can do, we can actually trace it back like this. So, you can go, we can take T inverse and then apply phi G and then apply T. So, that is going to give you a map from C n to C n. So, you take T inverse, apply phi G and then apply T. So, this is going to give you map from C n to C n. So, that we can actually think it as an action of G on C n. So, this actually allows us to define this new representation on C n. So, which is given by this, let us say xi, which is a map from G to GL of C n, where xi is given by G goes to T phi of G T inverse. But as far as the representations are concerned, we do not want to treat this as a new representation. So, for example, like we may be able to change again the basis. So, this is again some change of basis happened. So, if we change the basis again, so then say we have this b dash, then similar to this b. So, let us call this is xi b. So, we will have another map xi b dash. So, this map, let us say T b inverse. So, that is the map that is given here, T b inverse. So, then xi b dash of g is going to be T b dash phi of g and then T b dash inverse. So, we will have two new representations that is actually defined using the one that we started with, which is phi. So, but this phi, this xi b and xi b dash, all of them in a way they are all in a way same only. Okay. So, only the way on which the group element G acts. So, that is actually very explicitly given in terms of the basis. So, that means by changing the basis, so we do not expect the action to change. Okay. So, that means all these new representations that we obtain from phi, we want them to be like we want them to be called similar. So, that is how this equivalence of representations indeed obtained. But if you actually think about it, so this xi b and xi b dash, they are indeed similar, that means they are equivalent. So, you can just work it out that, so they are equivalent representations. So, how they are equivalent? So, let us see. So, if we just compute this xi b dash of g, so then that is exactly going to be by definition T b dash phi g T b dash inverse. So, T b dash phi g T b dash inverse, but recall that we have relation between phi and xi b. So, the xi b of g is exactly given by T b phi g T b inverse. So, we can substitute this phi g by this equation. So, if we do that, then we exactly get this is exactly equal to. So, let us rewrite this. If we rewrite this one, phi g is exactly equal to T b inverse xi b g and then T b. So, using this, if we rewrite this, you can easily see that this is exactly T b dash T b inverse xi b g and then T b dash inverse. So, basically if we take this capital S to be T b dash T b, sorry, this is supposed to be inverse T b inverse, then xi b dash of g is exactly equal to S xi b of g and then S inverse. So, S inverse is T b and then T b dash inverse. So, this tells us that we have this common capital S such that xi b g and xi b dash g, they are similar with respect to this common change of basis S. So because of that we can easily see that we can declare this xi b and xi b dash, they are indeed equivalent representation. So this is actually indeed the motivation behind defining the equivalent representations and defining the homomorphism of the representations of G. So let me just state it, what is the meaning of intertwining operator. So basically this S is indeed called the intertwining operator. So if we have two representation, let us call it phi from G to GL of V and then xi from G to GL of W. So then the intertwining operator S from V to W. So this satisfies the property that S of phi G of V should be equal to psi of G of S of V for all G in G and V in V. So this equation should be satisfied. So this is same as S composition phi of G is equal to psi of G composition S. So that means S phi G S inverse is equal to psi of G, and this is what called either homomorphism of G representations or intertwining operators. So basically the intertwining operators motivated from the change of basis that we see in the vector spaces, because once we have the action of the group, so by changing the basis the action of the group should not actually change. So that is the moral of the story. Okay. So I will stop here. So we will continue with the representation theory of finite groups in the next lecture. Thank you.